Good evening, everyone. You guys can't see me. This is a little different setup, but this is Matt Geary, the chair of the Pittsburgh Geo-Institute. I wanted to thank everybody for coming this evening, and, or attending, I should say. And before we get into the presentation, I did have a few business-related announcements. As you may have seen through email or the Pittsburgh section, all of the section events have been canceled for the rest of the program year, which conventionally ends at the end of the academic year in mid-April. So anything that was scheduled for the Pittsburgh section is basically canceled. Unfortunately, that also includes our short course, Quantitative Risk Assessment in Geotechnical Engineering, which was to be held on Saturday, April 4th. For those of you who are on and may have registered, we will be refunding. You'll be refunded, and you'll be refunded. And our plan is to host this short course next year, so you will get another crack at the content. The next two items on the list here actually go together. This will be my last event as the chair of the Pittsburgh Geo-Institute. And although it's been a challenge at times, I've genuinely enjoyed this opportunity. I've also especially enjoyed the program slate this year, some of which we had extremely good attendance, and they were all very engaging. Also, the response of the geotechnical community to the iRise program at Pitt was also very encouraging. We got quite a bit of responses to that, and hopefully in some way, shape, or form, that committee and the subsequent series of lectures will be able to follow next year. And as my last as chair, just kind of reflecting that it was definitely worth it. I've said this before and mean it, that there's really a special geotechnical engineering community here in Pittsburgh. And so as that ties in, and as you know, this is kind of the period at the end of one year. 6 years ago, I was starting off as a new board member at large, and the board is still looking for new members for next year. So if that's something that you think you'd be interested in, please reach out to myself or Shirley Tang at AGIS. And if you're interested in joining, I think a lot of the success that we had this year was due in large part to the hard work of our Geo-Institute board. It's been a great board, a lot of hardworking people, everybody pulling their weight, and so I'd be remiss if I didn't thank the board once again for all the hard work they put in. And, yeah, so thank you, board, those of you who are on the call. I also wanted to thank DFI, Mary Ellen, Teresa Engler, Katie Scully, all of these individuals, and especially Mary Ellen, really helped us pull this event together. She said, oh, it's not that big of a deal, it's easy, and maybe it was, but if they didn't have the hardworking crew to do the hard work to set this up, we wouldn't have been able to pull this off. And so I know when we looked at the program year, this topic was something that we really wanted to do, something we've really been looking forward to. And so the fact that we didn't have to cancel the event outright and could still have this webinar, that is due in large part to the work of Mary Ellen and her team. And also just reflecting, we kind of formalized this yearly cooperation with DFI maybe about 4 years ago, and really it's a great organization to work with. They have great content. They're a great partner organization, and speaking for myself and hopefully a lot of the other ASCE members, our partnership with the Deep Foundations Institute has been one that I hope has benefited both organizations. So thank you, DFI. I guess a little bit about the logistics and of this presentation and how there's questions and whatnot. I first wanted to start by saying that PDHs will be emailed to you by the Geo-Institute. So either Maria Jaime or Randall Booker, you'll get the PDH email, and that'll be based on the attendance list. I see we have around 50 people on right now. So at the end, we'll get an attendance list, and ASCE will mail you your PDH. So please do not reach out to DFI. They are not granting the PDHs for this event and will not be able to give you one. So those PDHs will come from ASCE, and like I said, Maria Jaime or Randall Booker. You may also see on your screen a gray dashboard, and on that dashboard there are some pop-out boxes, one of which is questions. If you pop out that questions dialog box, you can ask the question at any time as we're going through the presentation. Just type your question out, and it'll get queued up. And throughout the presentation, I believe Willie has two pauses throughout his presentation to answer questions, or just kind of like make sure everybody's caught up. There's not maybe a critical concept that was missed or needed addressed in the short term. And so we'll have those pauses throughout the presentation, and then at the end I will be reviewing questions and asking them to Willie, and then he can respond, so he's not trying to simultaneously queue up the next question and ask and answer one as well. So I think that's it for the logistics, and so I'll just get right in with Willie's introduction. Willie NeSmith is a licensed former chief geotechnical engineer for Berkel Company Contractors, who received his bachelor's degree from the Georgia Institute of Technology. His career has taken him to the Middle East and Africa, and it's those locations where he started to specialize in deep foundations. Willie is a leading authority in cast-in-place piles and has completed over 200 displacement pile projects nationwide. NeSmith has authored over 20 publications, is a past member of the Auger Cast-in-Place Piles Committee, and has served as the lead instructor for DFI's Auger Cast-in-Place Pile short course. So with that, I'm going to turn it over to our presenter, Willie NeSmith. Thank you, Willie.
You're quite welcome, Matt. The only problem with the introduction is you left off the emeritus part. And throughout my career, I've come across people who had that title, and I always thought it sounded pretty grand. But once it was applied to me, I started looking into what it actually means, and I enlisted the help of someone who had taken Latin in high school, and she informed me that emeritus literally means an old person who is not paid. So after 45-ish years of dedicated service to the geotechnical industry, that's what I have come to. Tonight's lecture is brought to you courtesy of the Deep Foundation Institute. It is part of the traveling lecturer series, although the lecturer hasn't been traveling much for the past few weeks. I did give a lecture at the University of Texas in Austin, and I had about 40 PhD and graduate students. And when I mentioned DFI, they sort of got a blank look, and I asked if anybody knew what the DFI was, and they didn't. And this far into my work with the DFI, I thought that was awfully strange. But then I reflected back on my experience. I graduated, the DFI was founded in 1976, which was the year after I graduated, but I was in the geotechnical consulting business for the next 25 years. And I heard a little about DFI, but never really looked into it. After I began to work for Berkel Company Contractors, I became a member of the DFI and got into it and found that I had been missing something. I had been working with deep foundation contractors for the previous 15 years. And when I got into DFI, I found that that's where I could interface with those guys in a meaningful way. And I was talking to Mary Ellen the other day, and one of their phrases is to find common ground, which I thought was terribly clever. But if you look at the pie chart, you can see that about a third of the members are contractors, but 25% are consulting engineers, some academics and some suppliers, and a small percentage of owners. And what I found was basically this is a place where everybody who's involved in the project can come together and find common ground. It's a unique opportunity for consulting engineers to interface with contractors and suppliers and the academic community. And I have found it a very rewarding organization to be involved in. This is a list that's too long to go through, but this is the technical committees and working groups that are a part of the DFI. Those highlighted in red are recent additions to the list. But if you take a quick scan through, you'll see that unless you're involved in some really obscure niche of geotechnical construction, there's something there that everyone can get involved in. So again, I encourage you to look into DFI. These are some upcoming events. Unfortunately, the international conference this month has been postponed, but as far as I know, everything else on here is still on. I particularly enjoy Superpile, which this year is from June 3rd through the 5th in St. Louis. And it is a really intense 2-day delve into deep foundation operations. And I've been involved in several of them. And if you're into deep foundations, you might find it, you will find it enjoyable. I understand that Gdansk, Poland is really nice in June if you're into deep mixing. And the annual conference on deep foundations is October 13th through 16th at National Harbor, Maryland. Hopefully we'll be back to some sort of near normal situation at that point. But that is a really, really interesting conference to go to if you're into geoconstruction of any sort. Just as an aside, as I said, I haven't been traveling much the past few weeks because of the COVID-19 issue, but I just wanted to pass on some regional information to you. I live in southern Georgia, about 30 minutes outside Savannah, and it's a rural area. And there are a lot of, I don't know, home remedy type things that go around in this area. And early in the COVID-19 situation, the word around the campfire was that if you consume a lot of alcohol, a great deal of alcohol, you could stave off the virus or at least mitigate its effects. And I can tell you, I've been practicing that regime, and it's worked well for me so far. So that's just again, a little regional information. Tonight's presentation deals with the use of cast-in-place piles in intermediate geomaterials. So basically, the way it lines up is we will talk about the evolution of cast-in-place piling equipment and processes, the definition of intermediate geomaterials, and then look at some examples, some example applications from a variety of geologic settings. The United States cast-in-place pile operation grew out of a pressure grouting process at a firm called Intrusion Prepack. And this firm was primarily involved in pressure grouting. Occasionally, in order to extend the grout pipe to where they needed to, they used a solid auger to auger through resistant areas. When that happened, they would drive the grout pipe down adjacent to the auger and then grout as they withdrew the auger. And I never could get a straight answer from Mr. Berkel about exactly who came up with the idea, but somebody somewhere thought, well, if we just turn this system vertically, we could build a cast-in-place pile. And they did. And a surprising number of structures, particularly in the Midwest, are founded on piles that were constructed using that process. And that is a solid auger drilled into the ground, an auger pipe driven in beside it, and then grouted as the pipe was withdrawn. So they worked on this process and, of course, determined that it would be better if they could pump the grout through the center of the augers, developed augers that would allow that, and then a patent was granted to Raymond Patterson for construction of cast-in-place piles by pumping through a hollow stem auger. Later on, licenses were granted to Lee Trezillo and Charles Berkel, and during that period, the late 50s and early 60s, there were 3 auger cast contractors in the United States. At the time these piles were coming onto the scene, the augers were advanced by relatively anemic power units, at least by today's standard. They generated about 15,000 foot-pounds of torque. The grout was batched on site using bagged cement, much like you would see a masonry contractor do today. So consistent production of even 3,000 PSI grout was a challenge. And installation of 5,000 linear feet of piling in a single day was considered a great accomplishment. At the time the auger pile industry was getting its legs under it, most of the deep foundations for major structures were supported by either driven piles or drill shafts. And probably most of you in the audience don't remember Raymond Concrete Pile Company but they had offices all over the United States. They were a driven pile company, and they basically owned several major markets. Into the 1970s, the augers were advanced by power units that developed around 30,000 foot-pounds of torque. ASTM 33 sand was used in grout mixes. That made a huge difference in the amount of grout that could be pumped and the pumps that were available to be used. Ready mix grout was common. I know any of you who have ever been on an auger pile site know that it arrives in a ready mix truck, but that only happened really during the 1970s. For most of you, that may sound like a long time ago, but for me, it's just like yesterday. A significant factor in the 1970s was the original patent for auger cast in place piles expired, and new installers began to enter the market. During the 1980s, at that point, there was a substantial knowledge base in the geotechnical community about auger piles. There had been continued advancement of the installation platform and grout delivery systems, and there began to be the application in what is termed intermediate geomaterials. And two of those applications that I'm going to talk about a bit tonight were the Miami Rapid Transit Systems, which was piles extended into soft limestone, and the Georgia World Congress Center, which were installed into partially weathered rock. And both of those projects were done with conventional crane-mounted equipment. Those were not necessarily the first projects that were installed into intermediate geomaterials, but they were landmark projects in their area, and those areas were large metropolitan areas. So they sort of served as a springboard for the use of auger piles in intermediate geomaterials. So for any of you who have been on an auger pile site, you sort of know what the pile looks like, the equipment looks like. There's a crawler crane with a set of leads mounted on it, and then the continuous flight hollow stem augers. There's a pump over to the side through which the auger, through which grout is pumped into the pile stem, and that's how the filling gets accomplished. I stuck this photo in because it's a good clean shot of a very large piling rig operation, but that's the way a conventional auger pile setup would look today. Beginning in the early 1990s, some European systems came into the US market, and they were fixed mast platforms that looked like the one in the photo here. They had a couple of features that were significantly different than the swinging leads crawler crane mounted platforms that I showed previously. Obviously a fixed mast here, mounted on a power system that is still crawler mounted, but these rigs were developed in Europe beginning in the 1960s for use with the European screw pile systems, which were significantly different from what was going on in the United States. One of the things that came over with these systems was data acquisition processes that really were not being used that much in the auger pile industry. In the auger pile industry, most of the focus was on the grouting operation, and by that time we had flow meters of some sort, and those have been improved, but the data acquisition systems in these fixed mast rigs was a significant difference from what had been going on. This photograph that's up now was from a piling operation that took place at the old Howard Hughes Airport in Los Angeles County. And it was the first cast in place system that was used in Los Angeles County. So the building officials required that we exhume a pile so they could look at it and make sure it looked like a pile, and this is it. All the water standing around is from the jetting operation that it took to get this pile out of the ground. But after it was exhumed, I was kind of happy because it shows up close and personal what the interface between cast in place piles and the adjacent material looks like. And the thing is, there is no smooth interface, and you can actually see the material that's adhered to the pile. And this is one of the reasons why cast in place piles can develop such high shaft resistance, is you're not limited by the resistance that can be developed at the interface. The failure surface or the movement actually occurs in the soil adjacent to that, adjacent to the pile. Those installation platforms that came over from Europe were significant in terms of the torque that was available, 150,000 to 200,000 foot-pounds. There's a plus there because these units are being improved all the time. I'm not sure 200 foot-pounds is even near the maximum torque now. The other significant item was that they were could develop 40 to 80,000 foot-pounds of crowd or downward force on the tooling, which cannot happen with conventional crawler crane mounted rigs. The only downward force you have is the weight of the tooling itself. Again, the other thing that came over with the European type fixed mast rigs was the ability to gather a great deal of information while the pile was being installed. And I'm going through these two different types because if you get into a pile installation in Intermediate Geomaterials, you may find contractors who are looking to use either conventional auger cast in place piling equipment, swinging leads mounted on a crawler crane, or fixed mast equipment. And there are pluses and minuses to both of them. One of the things that the contractor has to consider is the on-site logistics, and that's illustrated here. With a fixed mast rig, the rig needs to get roughly within 2 meters of the pile location. And in some cases that can be an insurmountable hindrance, whereas with a crawler crane, you can swing out and install a pile at a location where the fixed mast rig could never reach. So if you're getting into a piling operation, this is one of the things that the contractor has to think about. This fixed mast rig would never be able to reach that particular pile location. Just to look at the difference in the tooling that you might see between a conventional auger pile system, a relatively small stem, API threads. This is partial displacement system tooling. And again, I'm pointing this out because there are different applications that a contractor might want to use on any given site. This is a problem. There was a flash set in the grout, and that stem is entirely full of hardened grout and is going to have to be drilled out. So, Matt, if there are any questions up to this point, I'll be glad to field them. If not, I'm prepared to push on.
Willie, I don't see anything in the queue yet, but I did the DFI 45, the annual meeting. The conference chair is on the line, and he appreciates the plug you gave at the opening remarks there. So thank you for that, Willie.
Okay, no problem.
I also wanted to say it's kind of weird to tell a joke and not really be able to hear how it was felt, but I laughed on 2 occasions, so hopefully everybody else did too.
Well, I amuse myself a lot, so it's not a problem for me. Okay, we'll push on. So what are intermediate geomaterials? I don't know, some of you may have heard that term before, some maybe not so much, but I thought it would be good to go to the Federal Highway Administration to begin to get a definition of what that is. And so they talk about cohesive soil, granular soil, and then rock. And as the name implies, intermediate geomaterials, that's the stuff in between. For their definition, it's clay shales or mudstones with undrained shear strengths of 2.5 to 25 TSF. That's a pretty wide range. And cohesionless materials, granular tills, granular residual soils with an N value greater than 50 blows per foot. So that's kind of the material we're talking about here tonight, extending auger cast and place piles into. This chart is old, obviously, but it was one that was done by Kahawi and Foon in a 1993 publication, and it shows unit shaft resistance versus undrained shear strength or unconfined compressive strength. And so this circle or this feature outlines the general area where we're talking about. The upper end of what you would call the soil range and the lower end of what would be considered rock. So again, for reference, that's the area where we're going to be talking about tonight. So the types of intermediate geomaterials or IGMs, it's material that was either on its way to becoming rock, but didn't quite get indurated to the point that it could be called rock. Soft limestone, mudstone, clay shales, materials such as that. Materials that were once rock, but have been weathered to the point that they've lost some of their rock characteristics and obviously some of the strength that goes with the rock characteristics. Those are residual materials. And then there are materials that have been acted upon by some external physical or physiochemical processes that cause them to meet the criteria for IGMs, and that's broadly tills and marls. This item that's outlined here is significant in my experience, and it is a common feature of IGMs is difficulty in obtaining samples that reflect the character of the in situ mass. And throughout my career, that has been a problem for me. It's how to characterize the strength of these materials if you can't get a decent sample to take to the lab and test. And I don't have a solution for that. I'm just pointing out that that is a significant issue. So a few examples of intermediate geomaterials: vuggy limestone in South Florida, clay shales, sandstones, tills, and partially weathered rock. I've got Piedmont down there. Partially weathered rock exists in other areas, but the Piedmont occupies a fairly large swath of the East Coast, and it's an area, again, that I've had quite a bit of experience in. So that's why I have Piedmont included in that operation. So this is my interpretation of a typical Piedmont stratigraphy. I've included some fill because you seem to always run into that. The residuum, which is the material that has weathered from the underlying rock, and the typical Piedmont profile is maybe a little bit fine-grained near the surface, becoming coarser with depth, and then at some point you get into what is termed PWR, partially weathered rock, and using the Federal Highway Administration definition, this stuff normally falls into the intermediate geomaterial category. The penetration resistances start to exceed 50 blows per foot. And a key item is that it retains much more of the relic structure of the underlying rock. And in the Atlanta area specifically, that underlying rock could be granite, gneiss, schist, or a combination of those. So in the 1970s, as the auger cast in place pile industry was getting its legs under it and beginning to become a force in the marketplace, in Atlanta in particularly, and along much of the East Coast, most of the heavier, larger, higher structures were founded on caissons that were taken down to or into rock. As I mentioned before, Raymond piles were a large force in the marketplace during that time, and particularly in Atlanta. So you might find the larger, the really tall, heavy structures were on caissons to rock. The intermediate structures may have been on Raymond step tapered piles. Some of those may have gone to rock. But in the auger cast in place pile industry, they were stuck here with what they could get out of the residual. And that's why the development of the equipment and processes to be able to penetrate into partially weathered rock are so significant. Once those processes were developed, then the auger cast in place piles begin to displace the other systems. I'm not saying Raymond went out of business, but there are driven piles that are used in the Atlanta area, and certainly caissons are still used. But the go-to deep foundation system in the Atlanta area and a large segment of the Piedmont is now auger cast in place piles, because they can penetrate into that partially weathered rock, sometimes go down to hard intact rock. So that was a significant item in the Atlanta area and in the Piedmont in general. So what do you get when you are able to operate in the partially weathered rock zone or the intermediate geomaterial zone? Well, you get, if you look at this, this is a SPT profile in the Atlanta area, obviously in the Piedmont, and it's fairly deep. The residuum goes down to about 60 feet, where the penetration resistances start to kick up, and then they get into the 100 blow per foot range and just sort of stay there for until they reach refusal material. So if you look at the unit shaft resistances that you can develop, if you're hanging up here only in the residuum, you're at 0.75 tons per square feet. Maybe you go up to 1 ton per square feet per square foot in the lower part of the profile. But look what happens when you get into the partially weathered rock. That shaft resistance kicks up to, and 2.5 tons per square feet is not a limit. It's just it is a commonly used limit by some companies as to the shaft resistance that they will get behind for shafts in partially weathered rock. But you can see you basically get 2.5 times the resistance per square foot that you get in the residual. So getting down into partially weathered rock or an intermediate geomaterial has some real benefits in terms of load carrying capacity. Just to go back to this Kohawe and Foon chart. So this is shaft resistance. We're talking about 2.5 tons per square foot, which is here. And intuitively, at least to me, it makes perfect sense. It's better than soil, but not quite as good as rock. And that's where you're operating in the Piedmont in partially weathered rock or intermediate geomaterials. The other project that I referenced was the Miami transit system, which was done back in the 80s. And up to that point, drill shafts were the go-to system in Miami, and they knew a lot about the load carrying capacity of these limestone layers. And this is not a carved in stone, if you will, but this is a typical profile in the Miami area in particular. So the drill shafts had been typically used, but the Miami transit system project demonstrated to the local community, to owners and to the geotechnical engineers, that auger cast in place piles could penetrate into these materials, and they did so very successfully. This is a chart of side shear in tons per square foot versus unconfined compressive strength. and recall that it is difficult for most intermediate geomaterials to get a sample that you can take to the lab and test to determine the unconfined compressive strength. But in this case, that upper limestone, we were operating sort of in the 2 to 6 TSF range for side resistance. Down in the Fort Thompson limestone, we are operating in the 6 to perhaps 10 TSF range for side resistance. So you can see the advantage of being able to get to penetrate this intermediate geomaterial, get down into the Fort Thompson formation in terms of the capacity that you can develop. Going back to this chart again, just showing the range here of the materials that we're talking about in Miami or the South Florida experience. We've sort of encompassed this zone between soil and soft rock, but this stuff performs generally well into this soft rock area. Sorry, I skipped over something, and this is part of a paper that was produced in 2000, and it showed side shear resistance as a function of standard penetration test N values, and somehow they came up with linear relationships for the various formations. To me, this is just a good illustration of what you can get in intermediate geomaterials, and that is a wide scatter of standard penetration test values. So if you take that along with the fact that it's very difficult to get an intact sample that you can test, that's why intermediate geomaterials can be such a conundrum, not only for the cast in place pile industry, but also for the drill shaft industry. Just a photograph of a couple of rigs on a project in Miami. I think these were roughly 2-foot diameter piles, were being extended down about 100 feet. This particular power pack here is a conventional auger pile power pack. This one, this contractor got clever and extracted the turntable from one of the fixed mast European rigs and mounted it on a swinging lead operation. So this booger here has a lot more torque than this one. And then, you know, these contractors are clever. They want to do whatever they can to make a buck, and that's just a prime example. Just a photograph of what you see at the as the piles are being extended. Again, this is the European fixed mast rig turntable that was mounted on an auger pile rig. Just a lot of white material coming out, and a lot of times it's in the form of just gravel. Just a photograph of one of the cutting heads that was designed specifically for an IGM application. Again, what usually happens is the contractors develop these first, and they get manufacturers to come along and mass produce something like this, although some contractors prefer to use their own equipment. So what about shales? One of my favorite materials to work with. Highly dependent on local geology. That's a new thing for geotechnical engineering, isn't it? But shales are just that. They depend on the local situation, and I don't think you can take information from one geologic formation and extend it to another. So it is highly dependent on local geology. They may or may not be a transitional or weathered zone in the shale profile. Can be fissile or thick bedded, highly variable strength, and may be interbedded with hard limestone or sandstone that really can't be penetrated with the conventional auger cast in place pile equipment. So for me, a good place to start when looking at shales is GEC Geotechnical Engineering Circular number 8, section 5.3.3.3, a paper done by Vipulamanda. He likes to be called Vip, and I appreciate that. This was a 2005 paper that you can find the ASCE. But his method is based on the results of 8 load tests for piles socketed into clay shale with unconfined compressive strength ranging from 1 to 30 TSF. Now, those compressive strengths were determined based on Texas cone penetration test correlations with penetration resistance and unconfined compressive strength, another nod to the problems with dealing with intermediate geomaterials. But one of the interesting things about this process is that the capacity is given in terms of pile head displacement. So here are the 8 load tests that he ran. So what he does is go in and look at the range over which the relative load capacity, the load capacity is half of the ultimate load. So it goes in at 0.5 Q and looks at this relative displacement value here in terms of half of the ultimate load being mobilized. I tried and have in the past to sort out how these things fall, some rationale in terms of socket length or undrained shear strength of these materials. Sorry, let me go back. These cases 4 and 5 are the ones that show the stiffer response. Cases 1 and 2 are on the looser end of the response spectrum. So here are cases 4 and 5, and they fall in the socket range, L over D range of 4 to 5. Cases 1 and 2, they're sort of in that same range. If you look at this ratio versus undrained shear strength or unconfined compressive strength, excuse me, cases 1 and 2 are on the upper end. Cases 4 or 5 are kind of maybe in the middle here. All of that to say is I couldn't make any sense out of either socket length or unconfined compressive strength in terms of how these materials perform. But I do like the system, and I do want to point out this feature right here, and that's the minimum recommended L over D socket length for Texas Department of Transportation, and that is 3. and that is used quite extensively in the industry for sockets into intermediate geomaterials. Just an example of the using this process. When you first look at it, it seems a little convoluted, but basically here you take a 1.5 foot diameter pile drilled 4.5 feet into clay shale with an unconfined compressive strength of 20 TSF. You go through the process of finding, solving for this ratio, which is 0.79. There is an equation for ultimate capacity, which is calculated in this case as 276 tons. And the interesting part of this process to me is you, as the designer, then pick a pile head displacement and use this equation to come up with an allowable load, which is 170 tons, not an allowable load, a mobilized load capacity at the displacement you select. One of the issues with intermediate geomaterials and any materials that piles are extended into is, you know, how much shaft resistance and how much toe resistance is active at the displacement that I'd like to be working at. And the thing I like about this particular process is it takes that out of the equation, because that's already been cooked into the process. So you don't have to consider or worry about the toe contribution, and you select the level of pile head movement for the conditions that you're dealing with. Just another fallback or reference position, Federal Highway Department, Federal Highway Administration, micropiles guidelines has information related to some intermediate geomaterials. If you need some, if you're going into a new area and you need a starting point, this is a very good place to do that. That is the end of the presentation. Matt, I'll be happy to address questions if there are any.
Sure. So our first question was, what is the definition of partial displacement when you're talking about, you know, displacement pile, partial displacement piles, displacement piles? I think you'd be a great person to answer that, Willie.
Yeah. Let me go back to, okay. I showed this tooling because this, if a contractor shows up on a site with a fixed mast rig in order to extend it into intermediate geomaterials, or just to extend it into any soil materials, and he's going to do continuous flight auger operations, he will have tooling that looks like this. And this tooling goes back to the screw pile operations that emerged out of Europe in the 1960s. It is obviously much heavier. The connections are much beefier than the API connections. So I should have taken this partial displacement reference out, because many contractors will use tooling that, with a fixed mast rig, with tooling that looks a lot like this, in order to extend it into intermediate geomaterials. And this reference, this partial displacement reference, is to differentiate this from full displacement piling systems, which are almost never used in intermediate geomaterials.
Okay, one more question. Was, and I think you talked about it because you mentioned this after the question came in, but maybe elaborated on a little bit more. Was VIP, was he separating end bearing? Maybe just go through that again. I think the conclusion was his methodology bakes in end bearing, but maybe just review that one more time.
Okay, and I approach this from the standpoint of someone who was in the, a geotechnical consulting business for 25-ish years, and then went to work for a piling contractor. And it was always of interest to me how much of the capacity that I thought I was going to get came from shaft resistance versus end bearing. And, you can put in strain gauges and try to sort that out. But with intermediate geomaterials, it takes in usually so little movement to generate shaft resistance that you may not be able to confidently say how much toe resistance you're generating. So in my experience, again, particularly with intermediate geomaterials, materials that are much stiffer response than conventional soil materials, I always was concerned about how much of the capacity that I was looking at, how much of that ultimate capacity, if I add shaft resistance and end bearing, how much of that end bearing am I really generating? And again, one of the things that I like about the VIP system process that I talked about is that's taken out. I mean, that's already cooked into the soup. You don't have to worry about it. All you do as a designer is select a pile head movement that you want. And if you look at this chart, he has sort of, in selecting this Q over Q ultimate at 0.5, he's pretty much staying in the linear range. Okay, there's a little bit of bend in these looser materials, but he's pretty much assuring that he's going to be operating in the elastic area of these curves, kind of like using the conventional Davison limit for evaluating pile capacity. You're pretty much assured that you're staying in that you're going to be operating in the elastic range. So that comment was relative to my own difficulty with sorting out how much toe resistance I'm going to be developing if I've extended a pile through soft rock or intermediate geomaterial that has a very, very stiff response.
I have another question here, and I'm not sure that this is like a something that always is the case, but I know it seems like in one of your slides it was maybe referenced as sandstone as an intermediate geomaterial. Is it your understanding that that's sort of a global a global thing, or would that be more of like a local case, a weathered sandstone or something like that? The question
Yeah,
is just why is sandstone considered an intermediate geomaterial?
there are, and just it's more of a global thing. I mean, sandstone, one man's sandstone is another man's partially indurated rock, right? It's so poorly cemented sandstones can be penetrated. But if when someone says sandstone, if you think of something that would ring when you hit it with a hammer, that's not that's not material that's going to be penetrated. So there are sandstones which have been somewhat weathered and just left with enough of a connection between the grains to hold it intact, and it can be penetrated with an auger. Or there are sandstones like humate cemented sandstones that, you know, an old sandbar that was covered with vegetation and it rotted and it leaked a weak acid and dissolved some of the sand, and then it re-cemented. Those are the kinds of sandstones that I'm talking about. Again, this whole business with intermediate geomaterials is so geology and locale specific that I hesitated even to put sandstone up there. And there may be some people whose only experience with shale has been massive hammer ringing units, and that's not what we're talking about penetrating here. So I apologize if I have misled someone in this with this terminology, but we're talking about sandstone. Again, that's on the lower end of the strength scale.
Thank you. No, I mean, I think you stressed the local nature. That was a point that you hammered on at the very beginning. So, yeah, no, I think that's you hit that. Let's see here. So and this is probably a local experience, or reflects kind of the local conditions up here near Pittsburgh. The comment is that it could be risky to adopt this approach for intermediate geomaterials if the material changes with time due to weathering once it is exposed. You know, we have a lot of mostly like clay stones that, you know, you're getting 50/4, or you're getting 100 blows per foot penetration resistance, but you know, you can watch it just turn to dust if you let it sit out in the rain a couple of times. Do you have any experience with those types of formations, or any thoughts addressing rocks that weather very quickly?
I have experience with them, but defined quickly. I mean, you're going to drill a hole in the ground and fill it up with grout. So that material that is supporting the pile in shaft resistance and in bearing is no longer exposed to the weathering process. Now, the material at the top is going to weather, but I don't know if the geologic time frame we're talking about is enough for that to be a problem. I will say that there are materials that when just the introduction of the water that is in the grout that is used to fill the hole, or the concrete that's used to fill the hole in the case of drill shafts, changes the nature of that material. And again, that is why this is such a location specific process. You know, I'm not advocating that you go out and start ripping in auger cast in place piles all over Pittsburgh. What has been shown to be successful is a cooperation between the local contractors and the geotechnical community, where both sides are capable of some lateral thinking and doing some things that make sense. Obviously, contractors don't always take into account the geotechnical side of the issue, but particularly in Miami and Atlanta, those two places where the auger pile has become the go-to system where it previously was not. There has been an astute geotechnical community capable of some lateral thinking, and the contractor community that was capable of stepping out of their comfort zone. So that's the essence of the message here tonight.
Yeah, Willie, you were saying that, and I couldn't help but go back to your original graphic, your pie chart with the composition of DFI. So I think this just underscores that point and how this organization is, that it has a nice mix of people. And I think Pittsburgh is a place that, has a good group of both contractors and consultants and academics and whatnot. So I think we have that vibe going on here. At least I like to think that we do.
And that's important to be able to sit down in a relatively calm environment and talk to contractors. And I'm speaking with my geotechnical engineer hat on, to sit down and discuss problems or potential problems with a contractor and the suppliers. Don't leave those guys out of the equation, because sometimes the material that's being supplied is the issue that causes the problem. But if you can sit down in a committee room or at a conference with a contractor and supplier and have discussions, it helps. I have never seen anything very productive come out of an argument on site while piles or foundations were being installed. So it's much better to get it done ahead of time.
I think there's just maybe one more. How do you estimate settlement of auger cast in place piles bearing in intermediate geomaterials? And then the question is, this would be settlement of the intermediate materials within the pressure bulb below the tip of the pile.
That's done on the way you would do it for any other piling operation. In the Piedmont, and I didn't have this graphic, but Professor Paul Main at Georgia Tech has done a lot of work in determining, and it's done on a modulus basis. There is, you can't take a sample and run a consolidation test on partially weathered rock, but there's been a lot of pressure meter testing and that sort of thing to come up with modulus values for intermediate geomaterials, and that's basically the way settlement is addressed. And it would be the same for any foundation that is hung up in the partially weathered rock as opposed to going to rock. Somebody, and it's usually going to fall to one of you guys, has to come up with a modulus or a value to look at settlement. And all of the charts that I have shown, except for that last process, well, that doesn't address group settlement, only an individual pile settlement. But someone is still going to have to come up with a settlement estimate. And to tell you the truth, there are 30-story condominiums in Miami, which are founded in that lower limestone area, that have settled a couple of inches. Fortunately, the geotechnical community recognized that ahead of time, and it was planned for. So that question is very astute, in that just getting into intermediate geomaterial doesn't necessarily clean the slate with respect to settlement.
And then I think, at least for me personally, the one item that you kept going over that I was curious about and was hoping that you could speak to is, I think we all in this community recognize the difficulty in characterizing intermediate geomaterials through index tests. It really almost seems like the only thing you could do is really run tests and then kind of extrapolate that or use those results in the same formation throughout a given region. What would you say is the role of testing, like full-scale pile load tests, in kind of working out this issue and coming up with an economic design whenever the characterization may be challenging or uncertain of the material itself?
Matt, it almost has to come down to somebody being willing to do some pull-out test or small-scale testing in order to begin to draw a circle around what the response of the material is going to be. I mean, I know probably everybody out there has pulled up a split spoon sample in a weathered shale, and all you get out is a crumbles, a mix of rock fragments and soil. And what do you do with that? And what does that mean? It's really tough. It's a hard deal. You go in with a core barrel and you're going to get nothing. So you try to push a tube and you're going to get nothing. So I guess one of the things that I wanted to get across is the difficulty in assessing intermediate geomaterials. On the other hand, I wanted to get across the fact that the plus side of being to successfully characterize these materials can be huge in terms of capacities that can be generated. So I'm sorry, I don't have an answer for your question.
Okay. Well, thank you for that. And seeing no new questions and being at the time that we're at, I just wanted to wrap up and say thank you, Willie, and thank you, DFI. And yeah, I have a comment here about having you up for a Permanis lunch, a incline ride, and a baseball game. So
I was looking forward to it. Yeah, I was looking forward to that, and things have kind of gotten queered up a little bit. So maybe soon. I'm looking forward to getting back to Pittsburgh.
Okay, well, thank you again, and don't forget, everybody, PDHs will be coming through ASCE, not DFI. And yeah, thank you for attending today's webinar. Thanks again, Willie.
You're welcome.